Join us as we navigate the writing diagram and connection process for home lighting system.
Objectives. At the end of this session, you will be able to mount a solar panel for home lighting system and connect a DC home lighting solar PV system. Let's first look at the tools, equipment and materials needed for constructing a home lighting system. We will need tools, equipment and materials such as solar panel 260 watt 18.5 volt 1 number, battery 12 volt 40 ampere 1 number, solar charge controller 12 volt 10 ampere 1 number, DC cables, LED bulb 12 volt 9 watt 1 number, DC fan 12 volt 10 watt 1 number, DC DB with protective devices input side 1 number, DC DB with protective devices output side 1 number, multimeter 1 number, clamp meter 1 number, screwdriver, wire stripper, wire cutter and knife. First, let's explore the concept of home lighting systems or HLS. DC home lighting systems are commonly installed in various settings such as houses, temples, farmhouses, gardens, and more. One of the key advantages of these systems is their reliance on sunlight as a renewable energy source, making them both environmentally friendly and cost-effective. When setting up a solar photovoltaic module (SPV), it is important to consider the following factors. Choose an installation location that is free from obstructions like trees, buildings, or other structures that could cast shadows. Position the panels at azimuth angles and facing true south to maximize exposure to sunlight, taking into account the geographical location in India. Now, let's take a closer look at mounting structures. Mounting structures typically consist of frames and posts constructed from rust-resistant materials like steel. These structures provide sturdy support for the solar panels, ensuring they remain secure and stable. Careful attention should be given to the placement of the mounting structure to ensure optimal positioning for the solar panels. Next, let's see how we can install a mounting structure and solar PV panel. Begin by digging a pit of adequate depth and width at the chosen installation location. Ensure that the installation location has a sturdy wall, pillar, or foundation made of cement concrete to support the mounting structure securely. Determine the appropriate height for the mounting posts based on the site's specific requirements and conditions. Attach the posts firmly to the foundation using appropriate fasteners and techniques to ensure stability and longevity. Ensure that the mounting structure is installed perpendicular to the Earth's surface for optimal performance. Incline the surface of the solar photovoltaic panel towards true south with the appropriate inclination angle to maximize sunlight exposure. Once all conditions are met, securely fix the mounting structure in place using nails or cement concrete as per standard installation practices. Install the solar PV panel on the mounting structure at the designated location on the rooftop or field, following the provided guidelines for proper placement. Maintain a minimum wiring distance between the solar panel and the solar charge controller to minimize power loss. Ensure shorter wiring lengths from the solar charge controller to all loads to promote a balanced distribution of power. Incorporate individual switches to the different loads. Prioritize shorter wiring distances for the battery to optimize overall system performance. Connect the positive and negative wires of loads to the appropriate terminals of the SCC. Check the battery voltage using multimeter to check whether it is working well. Strip the two wires and crimp the lug to one end of the wire. Connect the red wire to the positive terminal and black wire to the negative terminal. Connect the red and black wires of the battery to the appropriate terminals of the SCC. Check the voltage of the solar panel using a multimeter. Connect the red and black wires of the solar panel to the appropriate terminals of the SCC. Switch on the SCC and check the loads by turning on individual switches. Next, let's see how we can integrate all the components to create an effective home lighting system. Take a moment to review the provided wiring diagram. In this setup, there are solar photovoltaic modules, SPV, solar charge controller SCC, battery, and loads, specifically 2 DC LED bulbs and a fan. For this demonstration, we will focus on the installation of a LED lamp and a DC fan on a table wiring setup. An essential step is to ensure the proper positioning of the SPV module. It is recommended that the SPV module be placed near the battery and charge controller. Mount the SPV module securely on a stable structure. Adjust the tilt and orientation of the SPV module to optimize sunlight. Safety tip: ensure that the installation site is safe with no risk of falling or accidents. After mounting the solar panels on the structure, connect the MC4 connectors from the DC cable to the panel. For this, align the male and female connectors and push them together firmly until they audibly click into place. This ensures a secure electrical connection. Now, we will bring the DC cable from the solar PV module to the input of DC distribution board. Begin by running the DC cable from the solar PV module to the location of the DC distribution board. Ensure that the cable is securely fastened and protected from any potential damage or hazards along its route. Take care to route the cable away from any sources of heat, sharp edges, or other potential sources of damage. Next, we will connect the DC cables to the DC-DB input protective device. Before making any connections, verify that the DC-DB switch is in the off position to prevent any electrical hazards. Connect the DC cables from the solar PV module to the input terminals of the DC-DB protective device, following the manufacturer's instructions and observing proper polarity. Ensure that the connections are tight and secure, and double-check for any signs of damage or wear on the cables or terminals. Now we will proceed to connect output terminals of DC-DB to the solar PV terminals of SCC with DC cables. Again, observe the correct polarity when making these connections to ensure proper operation of the system. Use appropriate DC cables suitable for the current capacity of the system and ensure that all connections are tight and secure. After making the connections, perform a visual inspection to confirm that there are no loose connections, exposed wires, or other potential safety hazards. Before connecting the battery to the SCC, it is crucial to verify its voltage to ensure it is within the acceptable range for the system. Once confirmed, connect the positive and negative terminals of the battery to the corresponding terminals on the SCC. Connect the load terminals on SCC to the input terminals of output DC-DB with DC cables by observing correct polarity. Connect the wires from the loads, LED lamp and DC fan to the output terminals of the output DC-DB. Make sure the DC-DB switch is off. Safety tip: ensure the output switches of the DC-DB are in off condition and ensure firm wire connections to the terminals on SCC. Make sure the wire strands do not protrude outside. It is essential to double-check that the wiring matches the correct polarities to avoid any potential damage. Take time to inspect each connection thoroughly, rectifying any errors or loose connections found. Once everything is in order, first turn on the input DC-DB and then turn on the output DC-DB. Test each load individually using the DC-DB output protective device. Monitor the current and voltages flowing through the solar and battery cables to ensure proper operation. Please note that at night time, the SCC uses battery to power the loads. In other words, if input DC-DB is off, simulating the night condition, and output DC-DB is on, the loads still powers on. It is important to note that the loads in our system can be customized according to specific requirements, allowing for flexibility and versatility in meeting varying lighting needs.
This brings us to the end of the session. In this session, you have learned to connect a DC home lighting solar PV system and mount solar panel in rooftop for home lighting system. Thank you for watching. See you in the next session. Hello and welcome to this session. In this session, we will begin a journey to master the installation and commissioning of a solar water pump. Join us as we explore the components, installation procedures, and operational insights to ensure a successful setup.
Objectives. At the end of this session, you will be able to construct and test a solar water pump.
Let's first look at the tools, equipment, and materials needed for constructing and testing a solar water pump.
We will need tools, equipment, and materials such as solar PV module 335 watt 38.16 volt 2 numbers, BLDC motor pump set 750 watt 48 to 72 volt DC 1 number, steel water tank with plumbing pipes 2 numbers, control panel with digital DC voltmeter 1 number, digital DC ammeter 1 number, DC MCBs 2 numbers, DC terminals and patch cords, spanners, knife, screwdriver, multimeter, and DC clamp meter. Next, let's see and learn about what kind of environment is required for installing a solar water pump. Creating an optimal environment for solar pump installation is vital to maximize sunlight exposure, ensure efficient energy generation, and ultimately enhance the overall performance and sustainability of the system. A perfect setting for erecting solar panels would be in a vast open agricultural area with the sun beams down from above illuminating the landscape. Next, we need to identify the location to install the water pump. Selecting and preparing the location for our solar pump system is crucial for optimal performance. Being close to a natural water source is crucial for reducing energy loss due to lengthy cables and ensuring optimal system performance. It is also essential to ensure that the selected area is free from any obstructions such as trees or buildings that could cast shadows on the solar panels. Civil work plays a crucial role in the installation process of the solar panel system, ensuring a sturdy foundation to support the mounting structure and the weight of multiple SPV modules. The civil work involves several essential steps. Firstly, prepare the pit for the mounting structure and electrical ground point, ensuring proper placement and alignment for optimal functionality. Next, prepare the cement concrete, meticulously mixing and pouring it into the pit to create a solid and durable foundation. Finally, erect the structure, carefully assembling and securing it in a place atop the foundation, ready to support the array of SPV modules. The selection of the solar panel specifications should align with those of the pump based on its requirements. Next, ensuring a robust foundation through meticulous civil work is paramount for the successful installation of the solar pump system, facilitating optimal performance and longevity amidst varying environmental conditions. In addition, it is imperative to execute the essential plumbing work to ensure seamless functionality of the system. This determination would dictate whether a series or parallel connection is necessary to activate the pump. An appropriate pump controller needs to be selected for this system. Next, let's see how to connect the various components for a solar water pump system. We will connect components such as solar panel, pump, and pump controller to provide a comprehensive understanding of their integration. For this demonstration, we will be using 335 watt solar panels connected in parallel, 1 HP DC water pump, and a pump controller. As mentioned earlier, all these components are installed in their respective locations. First, Identify the wires of the solar panels and connect them to the MC4 connectors. Attach the red wires to the male MC4 connector and the black wires to the female connector. This ensures proper polarity. With the pump controller in place, it is time to wire up the water pump. Make sure all connections are secure and properly insulated. During this process, be prepared to extend wires if necessary and complete any required plumbing work to ensure smooth water flow. Before making these connections, ensure that the cables from solar panel are not connected to the pump controller. This prevents from shock. Finally, connect the solar panel's cables to the pump controller and flip the switch. Watch as water flows from the pump, a testament to our carefully crafted connections. Next, let's see an alternative approach to showcasing the electrical connection of all the devices. This approach will offer a fresh perspective on the electric connection phase beyond the traditional method depicted earlier. This is the block diagram of the control panel where the solar panel and pump are going to be connected. The necessary circuit breakers will also be incorporated here. Ammeters and voltmeters are added on the solar panel to check the voltage and current. First, let's locate the two solar PV modules. Each module has a rating of 335 watts and is already installed. Our next task is to identify their corresponding wires. Next, we need to carefully connect these wires to the control panel. They need to be connected in series to meet the specifications of the BLDC motor pump set. This set requires 750 watts of power, so precision is important here. Safety tip: before proceeding, ensure that all load switches are in the off position to prevent any accidental activation during the setup process. Next, we will take the connected wires of the solar PV module and securely attach them to the appropriate positions on the control panel. Carefully handle the connected wires from the solar PV module, ensuring they are free from any tangles or knots. Inspect the designated positions where the wires will be attached in the control panel. Align each wire with its corresponding terminal on the control panel, taking care to match polarity correctly to avoid any potential short circuits or damage to the system. Once aligned, we will securely fasten each wire to its terminal, making sure all connections are tight and secure. Now let's proceed to connect and configure the DC voltmeter and DC ammeter of the control panel to measure the solar panel current and voltage. Begin by carefully attaching the positive and negative terminals of each meter to the corresponding terminals on the control panel. Ensure a secure connection to avoid any inaccuracies in readings. The next step would involve the connection of the second circuit breaker. This connection ensures proper distribution and management of electrical power within the system. Subsequently, additional wires from the pump can be connected as needed to complete the circuit and enable the pump's operation. Now let's take a moment to highlight the components of our pump system. It comprises of controller units designed to oversee and regulate both the interface and speed, enhancing the efficiency and performance of the entire setup. Make necessary connection to power up the water pump. Before we proceed further, let's ensure that our system has access to the essential source it needs, that is water. We will verify that the bottom tank serving as our natural water source is adequately filled and ready for operation. After all connections are made, carefully turn on the switch or load of the system, ensuring that all connections are in place and intact. Now it's time for a thorough testing of the system. We will utilize the precision instruments available in our control panel, the DC voltmeter and DC ammeter, to meticulously examine both currents and readings. This thorough evaluation ensures that our system is operating within desired parameters and provides valuable insights into its performance and efficiency. As the system is activated, observe water is pumped from the bottom steel tank to the upper steel tank. This confirms that our system is working perfectly. Note that this water pump system operates exclusively during daylight hours and does not require a battery.
This brings us to the end of this session. In this session, you have learned to select an optimal location for solar water pump system, construct and install a solar water pump, and test the solar panels post-installation. Thank you for watching. See you in the next session.
Step 3. To the bottom left and connected to the bus is another fixed circuit breaker. There is an automatic transfer switch symbol. Also notice that a circle symbol which represents an emergency generator is attached to the automatic transfer switch. A low voltage motor control circuit is attached to the automatic transfer switch through a low voltage bus. On the right side of the third area, there is another fixed circuit breaker connected to the bus. It is attached to a meter center as indicated by the symbol formed by 3 circles. Below the meter center is a load center or panel board that is feeding a number of smaller circuits. This could represent a load center in a building that feeds power to any electrical equipment connected to the building. This table shows universally accepted electrical symbols to represent the different electrical components and their meaning within a circuit or system. These help in interpreting SLDs and understand the electrical symbols. The following are the major electrical substation equipment. Instrument transformers is a static device utilized for reduction of higher currents and voltages for safe and practical usage, which are measurable with traditional instruments such as digital multimeter, etc. Current transformer (CT) are generally used to measure currents of high magnitude. These transformers step down the current to be measured so that it can be measured with a normal range ammeter. Potential transformers (PT) are also known as voltage transformers, and they are basically step down transformers with extremely accurate turns ratio. Conductors. A conductor is a material that has many valence electrons, permitting electrons to move through it easily. Generally, conductors have many valence shells of 1, 2 or 3 electrons. Most metals are conductors. Some common good conductors are copper, aluminium, zinc, lead, tin, eureka, nichrome, etc. Whereas silver and gold are very good conductors. Insulators. An insulator is a material that do not permit flow of electrons through it. Generally, insulators have full valence shells of 5, 6 or 7 electrons. Some common insulators are air, gas, rubber, plastic, paper, porcelain, PVC, fiber, mica, etc. Isolators. An isolator is a switch. These cannot be used for automatic tripping. Isolators are not meant for either closing or breaking the circuit on load or short circuit. Bus bars. The bus bar is among the most important elements of the substation and is a conductor which carries current to a point having numerous connections with it. Lightning arresters are the protecting equipment of substation from high voltages and are also limiting the amplitude and duration of the current's flow. Circuit breakers. A circuit breaker is a mechanical switching device capable of making, carrying and breaking the currents under normal condition and breaking the currents under abnormal conditions like a short circuit. Relays. A relay is a device which opens or closes an auxiliary circuit under predetermined conditions in the main circuit. Capacitor banks. The capacitor bank is defined as a set of numerous identical capacitors which are connected either in parallel or series inside an enclosure and are utilized for the correction of power factor as well as protection of circuitry of the substation. Batteries. Some of the important substation parts such as emergency lighting, relay system, and automated control circuitry are operated through batteries. Wave trapper is placed on the incoming lines for trapping of high frequency waves. Distribution feeders transport power from the distribution substations to the end consumer's premises. The feeders run along streets overhead or underground in some cases and power the distribution transformers at or near the customer premises. Here is a schematic representation of the substation. Connecting the non-conductive metal body or parts of an electrical equipment and system to the earth through a low resistance conductor is called as earthing. Earthing of an electrical installation can be brought under two major categories: system earthing and equipment earthing. Let us know about the system earthing. Earthing associated with current carrying conductors is normally essential to the security of the system and is generally known as system earthing. System earthing is done at generating stations and substations. Equipment earthing is nothing but earthing of non-current carrying metalwork and conductor, which is essential for the safety of human life, animals, and property. Now that you are familiar with the transmission and distribution substation, we have few tasks for you to check your understanding. To do the task, be prepared with the following required items: drawing sheet, pencil, eraser, and scale. The instructor may take the trainees to the nearest transmission or distribution main substation and explain the name of the equipment, their specification and function. Also instruct the trainees to follow the safety regulation while visiting the substation. Your first task is to visit the transmission and distribution main substation, identify the sequential stages of transmission or distribution substations, trace and identify the various equipment like transformers, feeders, circuit breakers, isolator, CT and PT, etc. from the generator to the consumer points in sequence of transmission and distribution substation. Note down the earthing system. The major substation is provided with system earthing. Note the different values of earth resistance displayed in the earth pit. Note down which equipment or installation requires the least earth resistance value and irregular value. Identify the hollow conductors used for connection between feeders. Enter the details in the given table format. Your second task is to locate the places of equipment and draw the single line diagram of transmission and distribution substation which you have visited and get it checked with your instructor. These are the diagrams for your reference.
We have reached the end of this session on visit to transmission or distribution substation. By now, you should be able to know the transmission network of India, describe the transmission and distribution substation, explain a single line diagram, list the electrical substation equipment, visit and trace the transmission and distribution line of substation, identify the equipment in sequential stages of distribution substation, and prepare the layout and draw the single line diagram of the transmission and distribution. In this session, we will be learning how plot sun chart and locate the sun at your location for a given time of the day. At the end of this session, you will be able to know the division of energies, explain and differentiate between non-renewable and renewable energy sources, and describe the seasonal changes and sun path.
Energy is the amount of work that can be performed by a particular force. It can be transferred into other areas and objects, but the energy quantity always remains the same. Different forms of energy include thermal, kinetic, potential, sound, and light energy. Fundamentally, there are two types of energy: potential and kinetic energy. Potential energy is the energy of a body or a system due to the position of the body or the arrangement of the particles of the system in a force field. Kinetic energy is defined as the work needed to accelerate a body of a given mass from rest to its stated velocity. All the forms of energy can be broadly divided into two main subgroups: renewable and non-renewable energy. Non-renewable energy will eventually run out and cannot be replaced. Examples are fossil fuels such as oil and natural gas. Renewable energy can be obtained for an unlimited time period. Examples are solar and wind energy. Renewable resources are replenished naturally, which means they will never run out. The major renewable energy sources are solar energy, biomass, wind energy, geothermal energy, and hydropower energy. Solar energy is the heat and radiant light from the sun that can be harnessed with technology such as solar power and solar thermal energy. Biomass energy derives its energy from plant materials. Wood is the most common and still the largest biomass energy source. But breakthroughs in research have increased biofuel to encompass food crops, algae, and industrial waste to make biomass. Biomass materials harness the power inside the plant matter to make this energy. Wind is the movement of air caused by the uneven heating of the earth by the sun and the earth's own rotation. Winds range from light breezes to natural hazards such as hurricanes and tornadoes. Geothermal energy is thermal energy generated and stored in the earth. The geothermal energy of the earth's crust originates from the original formation of the planet and from radioactive decay of minerals. Hydropower energy is a form of energy that harnesses the power of water in motion to generate electricity. Like other types of renewable energy, this doesn't create any smoke and hence doesn't cause any form of pollution. Moreover, today it's highly possible for homes to generate their own hydroelectric power using small hydros without building huge dams. As you are now familiar with the different forms of energy, their divisions, sources, and the relationship between Earth's orbit and sun path, let us have a look at few tasks to check your understanding. Your first task is to identify the non-renewable or renewable energy sources in this table. Your second task is to study the nature and analyze how does solar energy influence the other renewable energy. Solar energy is much more effective and versatile than wind power as it can be deployed close to load centers, thus reducing burden on transmission lines. Solar plants do not modify the environment and can be built in a few months as compared to hydropower plant. Photovoltaic cells are superior compared to biomass as they do not occupy fertile land that could be used for crops. Geothermal energy can only be used as a heating and cooling solution, while solar energy can generate electricity with photovoltaic PV technology. Also, geothermal power plants emit small amounts of carbon dioxide, unlike solar energy. The final task is to analyze the availability of sunlight on your place based on observations made during the day, the month, the season, and throughout the year.
We have reached the end of this session on plot sun chart and locate the sun at your location for a given time of the day. By now, you should be able to know the division of energies, explain and differentiate between non-renewable and renewable energy sources, and describe the seasonal changes and sun path. In this session, we will be learning how to find out relations between sunlight and earth motion by globe model. At the end of this session, you will be able to know the nature of solar radiation and variation in its reception on earth due to different causes using globe model, and light source, explain the earth and sun planets motion as well as its implications in maximizing solar energy utility, and get familiar with latitude and longitude for a given location.
Sun paths at any latitude and any time of the year can be determined from basic geometry. The Earth's axis of rotation tilts about 23.5 degrees relative to the plane of Earth's orbit around the Sun. As the Earth orbits the Sun, this creates the 47 degrees declination difference between the solstice sun paths as well as the hemisphere-specific difference between summer and winter. In the northern hemisphere, the sun path near to the winter solstice rises in the southeast, transits the celestial meridian at a low angle in the south, and then sets in the southwest. The sun path is on the south equator side of the house all day long. A vertical window facing south equator side is effective for capturing solar thermal energy. For comparison, the sun path near the winter solstice in the southern hemisphere rises in the northeast, peaks out at a low angle in the north, and then sets in the northwest. Duration of daylight. North of the Arctic Circle and south of the Antarctic Circle, there will be at least one day a year when the sun is not above the horizon for 24 hours during the winter solstice, and at least one day when the sun is above the horizon for 24 hours during the summer solstice. The angle of incidence of the solar radiation is changing continually as the Earth is circling around the sun and also spinning around its own axis. The 23.5 degrees inclination of the Earth's axis also has an influence as shown. The Earth is not a flat disk. It is almost spherical in shape, and gravitational force binds the atmosphere like a shell. The intensity of the solar radiation at a point on the surface is therefore influenced by the curvature of the surface and the effective thickness of the atmosphere. Accordingly, the installation angle varies from season to season depending on a geographical location. Let us learn about the rise and set directions. On the northern hemisphere, the north is to the left, the sun rises in the east, culminates in the south while moving to the right and sets in the west. Both rise and set positions are displaced towards the north in summer and towards the south for the winter track. On the southern hemisphere, the south is to the left, the sun rises in the east, culminates in the north while moving to the left and sets in the west. Both rise and set positions are displaced towards the south in summer and towards the north for the winter track. On the imaginary line of the equator, the sun maximum elevation is great during all the year, but it doesn't form every day a perfect right angle with the ground at noon. In fact, it happens 2 days of the year during the equinoxes. Summer days are longer than winter days, but approximately the difference is no more than only 2.5 hours. Azimuth angle of the sun is defined as the angle from due north in a clockwise direction. Zenith angle of the sun is defined as the angle measured from vertical downward. Angle of inclination of radiant light and its relation with latitude and longitude of different locations on Earth. Depending on a geographical location, the closer to the equator, the more potential solar energy is available. The Earth reaches the point nearest to the Sun in the beginning of January each year. After 6 months, on the 4th of July, it reaches the farthest distance from the Sun. Due to these different distances, the direct solar radiation reaching the Earth's atmosphere is 7% more intense in January than it is on the 4th of July. These differing distances between the Earth and the Sun only have a minor effect on the seasonal temperatures on the Earth. It is time to test your understanding. You need a candle or electric bulb or torch and a rotating globe model. Your task is to study the given diagrams, which is a pictorial representation of Earth's path around the Sun, and record your understanding.
We have reached the end of this session on Find out relations between sunlight and Earth motion by globe model. By now, you should be able to know the nature of solar radiation and variation in its reception on Earth due to different causes using globe model and light source explain the Earth and Sun planets' motion as well as its implications in maximizing solar energy utility, and get familiar with latitude and longitude for a given location. In this session, we will be learning how to observe on globe which countries are in the northern hemisphere and which are on the southern hemisphere. At the end of this session, you will be able to know the northern and southern hemisphere and find out the countries in northern and southern hemispheres.
The equator of the Earth splits the Earth into roughly two equal parts, which are known as hemispheres. The two hemispheres have opposite seasons and the night sky can look very different. The northern hemisphere is the northern half of the Earth that starts from 0 degrees latitude to 90 degrees north, forming the North Pole. The southern hemisphere is the southern half of the Earth that starts from 0 degrees latitude to 90 degrees south, forming the South Pole. Have a look at the world map showing the northern hemisphere constituting 87% of world population, thus forming the largest portion of land mass on the globe. 5 of Earth's 7 continents are either wholly or partly in this hemisphere. This includes complete North America and Europe, most of Asia, 2/3 of Africa, and the northern part of South America. There are more countries in the northern hemisphere than in the southern hemisphere, which includes the 3 largest countries by population: India, China, and the United States. Russia is the largest country geographically. It makes up for roughly 11% of the Earth's total landmass. 4 of the 5 world oceans are present in the northern hemisphere: the Pacific, Arctic, Indian, and Atlantic Oceans. Here you can see the southern hemisphere consists of more ocean than the northern hemisphere and having only 13% of world population. The continents Australia and Antarctica are located completely in the southern hemisphere. Also, most of South America and 1/3 of Africa are in the southern half of the globe. The most populated country south of the equator is Indonesia, while Brazil is the largest country geographically. Traditionally, Australia and New Zealand have been considered more western countries in the southern hemisphere. The Southern Ocean is the only ocean that is located entirely in the southern hemisphere. Except for the Arctic Ocean, the other 4, the Pacific, Indian, and Atlantic Oceans, are also present in the southern half of the globe.
Seasons in the northern and southern hemispheres are opposite. When it is winter in the northern hemisphere, it's summer in the southern hemisphere. This is because Earth's axis is tilted in relation to its orbit around the Sun, known as axial tilt. Each hemisphere tilts toward and away from the Sun at opposite times of the year. So, when it is winter in the northern half of the globe, it is summer in the southern half and vice versa. Astronomical spring in the northern hemisphere starts with the March equinox, summer with the June solstice, fall, autumn with the September equinox, and winter with the December solstice. The northern hemisphere receives more sunlight between March and September, and the southern hemisphere receives more sunlight between September and March. The seasons are unequal in the northern and the southern hemisphere. For example, summers in the northern hemisphere are a few days longer than summers in the southern hemisphere. This is because the Earth is slightly further away from the Sun in July than in December and moves more slowly in its orbit around the Sun. Now that you are familiar with the northern and southern hemispheres, let us do few tasks to test your understanding. You need a globe model or world atlas to perform the task. Your first task is to find out the countries in the northern hemisphere and record in the table. Your second task is to find out the countries in the southern hemisphere and record in the table.
We have reached the end of this session on Observe on Globe which countries are in the Northern Hemisphere and which are on the Southern Hemisphere. By now, you should be able to know the Northern and Southern Hemispheres and find out the countries in Northern and Southern Hemispheres. In this session, we will be learning how to prepare a list of places around India, their latitude and longitude. At the end of this session, you will be able to know the latitude and longitude and find out latitude and longitude of different cities in India.
Let us learn about the latitude and longitude. Latitude and longitude are parameters or coordinates that help determine the location of any place on Earth. Both latitude and longitude are angles that uniquely define points on the Earth's sphere. They constitute a coordinate system or scheme to locate or identify geographic positions anywhere on the Earth's surface. Together, latitude and longitude enable cartographers, geographers, and others to locate points or places on the globe. They also show the angular distance of any place from the Earth's center. Latitude and longitude are both measured in degrees and minutes. Latitudes are horizontal lines known as parallels that measure distance north or south of the equator. Latitude lines are a numerical way to measure how far north or south of the equator a place is located. The equator is the starting point for measuring latitude. That's why it's marked as 0 degrees latitude. The number of latitude degrees will be larger the further away from the equator the place is located, all the way up to 90 degrees latitude at the poles. Latitude locations are given as dash degrees north or dash degrees south. Longitudes are vertical lines known as meridians that measure east or west of the meridian in Greenwich, England. Longitude lines are a numerical way to show or measure how far a location is east or west of a universal vertical line called the prime meridian. The vertical starting point for longitude, the prime meridian, is numbered 0 degrees longitude. To measure longitude east or west of the prime meridian, there are 180-degree vertical longitude lines east of the prime meridian and 180-degree vertical longitude lines west of the prime meridian. So longitude locations are given as dash degrees east or dash degrees west. The 180-degree line is a single vertical line called the international date line, and it is directly opposite of the prime meridian. A place in the northern hemisphere is identified by its northern latitude and assigned a suffix of N for north. The latitude of the Tropic of Cancer is expressed as 23 degrees 26 minutes north or 23 degrees 26 north. Similarly, the Arctic Circle, which is nearer to the North Pole, has a latitude measure of 66 degrees 34 minutes north. Latitudes in the southern hemisphere are assigned a suffix of S for south. Thus, the Tropic of Capricorn, the horizontal imaginary circle below the equator, has a latitude of 23 degrees 26 minutes south, and the Antarctic Circle, a horizontal circle further below the equator and nearer to the South Pole, has a latitude measure of 66 degrees 34 minutes south. Latitudes north of the equator are denoted by positive values, while those in the south are assigned negative values. Latitude angles can range up to plus 90 degrees or 90 degrees north, and down to minus 90 degrees or 90 degrees south. It's interesting to note that the Tropic of Cancer and Tropic of Capricorn have the same latitude measure. This is because they are both horizontally equidistant from the equator. The only difference is that the Tropic of Cancer is in the northern hemisphere, so its latitude is expressed as 23 degrees 26 minutes north, while the latitude of the Tropic of Capricorn in the southern hemisphere is expressed as 23 degrees 26 minutes south. The same goes for the Arctic Circle and the Antarctic Circle. Let us see how to read latitude values. There are three different types of latitude: geocentric, astronomical, and geographic. The geocentric latitude is the most referenced one, expressed in degrees and minutes, and sometimes also in seconds. The geocentric latitude refers to the angle subtended by an angle at the Earth's center and is always expressed in a north-south plane from the equator. Cairo has a latitude of 30 degrees 3 minutes north, subtends an angle of 30 degrees 3 minutes at the center of the globe. North indicates that Cairo is to the north of the equator and therefore in the northern hemisphere. Dunedin, New Zealand has a latitude of 45 degrees 52 minutes south, meaning it subtends an angle of 45 degrees 52 minutes at the center of the globe and lies in the southern hemisphere. The prime meridian divides the Earth into its eastern and western hemispheres. Longitudes provide the location of a place that's east or west of the prime meridian. Longitudes are also measured in degrees and minutes and sometimes in seconds. All longitudes are measured from the angle they make with the center of the Earth based on the intersection of the equator and the prime meridian. Now let us see how to read longitude values. All longitudes other than the prime meridian are measured by up to 180 degrees both east and west of the prime meridian. For example, the longitude of Los Angeles is 118 degrees 15 minutes west. This indicates that Los Angeles is 118 degrees and 15 minutes to the west of the prime meridian. Los Angeles is in the western hemisphere. The longitude of Mumbai, India is 72 degrees 50 minutes east, indicating that Mumbai is 72 degrees and 50 minutes to the east of the prime meridian. Mumbai is in the eastern hemisphere. Here we will learn how to read both latitudes and longitudes. Every location on Earth is expressed in terms of its latitude and longitude values. Together, the circles of latitude and meridians of longitude show where a particular place is located on Earth with reference to the prime meridian and the equator. Example 1. A point described as 59 degrees 57 minutes north and 10 degrees 45 minutes east is located 59 degrees and 57 minutes north of the equator and 10 degrees and 45 minutes east of the Greenwich meridian. This location is Oslo, Norway. Example 2. Montreal, Canada is expressed as 45 degrees 30 minutes north and 73 degrees 34 minutes west. These coordinates show that Montreal is 45 degrees 30 minutes north of the equator and 73 degrees 34 minutes west of the prime meridian. Example 3. Papua New Guinea is in the southern and eastern hemispheres. That's why the coordinates of its capital city, Port Moresby, are expressed as 9 degrees 31 minutes south and 147 degrees and 13 minutes east. As you are now familiar with the latitudes and longitudes, let us do a task to test your understanding. You require a globe model or world atlas to perform this task. Your task is to check on the India map or globe model over India and select few city names from all regions. Find out their latitude and longitude. Append the findings in the table.
We have reached the end of this session on prepare a list of places around India, their latitude and longitude. By now, you should be able to know the latitude and longitude and find out latitude and longitude of different cities in India.
In a few minutes, I will be briefing on the topic soil stabilization techniques with prefabricated vertical drain. The purpose of the PVD technique